teamwork, out-of-the-box thinking, and evolving strategies. These aren't just human traits anymore. Today, I'll show you how a simple child game helped AI agents learn all of these skills and what we can take from it. The study I concluded seeks to demonstrate that complex human-level skills can emerge in AI purely from the interplay of competition and self-motivated adaptation. If successful, this approach could represent a powerful, scalable method for building highly capable agent AI that can autonomously learn and adapt in unstructured environments. One of the long-standing goals in AI research is to build agents capable of handling diverse human-level tasks. Traditionally, teaching agents complex skills in a supervised manner requires carefully crafted neurological structures, which is often impractical for real-world applications. Which is why we aim to know here if AI can develop autonomously those skills with little programming, using competition as an incentive. Another topic that we'll see throughout the presentation is the interaction between agents. The child game I talked about earlier that we'll use for the study will be hide and seek. As it's team-based, AI agents will be forced to team up to handle tasks that cannot be done alone. We'll see that the layouts of the maps for the hide and seek game will change throughout the study. From this, we can further study how AI can use prior knowledge that they learn on other maps to adapt to new ones, and how competition mixed with broad objectives, being hiding if you're in the hiding team or seeking, um, can encourage to develop complex skills. The agents are tasked to compete in a two-team hide-and-seek game. The game is physics-based to mimic real life. There are randomly generated objects scattered throughout the map. Both teams can decide to move them around. An interesting twist is that only the hiders can choose to lock them in place. We'll see strategies developed around this mechanic. And the maps are randomly generated. That makes it so that I can run multiple instances of levels to have further iterations of the game to make more observation. Here you can see how the game plays out in three different randomly generated layouts. The objects mainly consist of cubes, ramps, and long walls. You can see the hiders having the preparation phase, moving around objects, and locking them in place to win the game. As the agents train against each other, there are as many as 4 different strategies that emerge, each of which create a new pressure for the opposing team to adapt to. Note that there are no direct incentive for the agents to explore the layouts or to use objects, making the strategies a result of self-driven learning induced by the competitive nature of multi-agents environments. The first tactic developed is fort building. It took only 8.62 millions of iterations. We can associate that to shelter construction. Next, the seekers learned to use the ramps after 14.5 million iterations. We can associate that to tool use and problem solving. We can clearly see that the agents learn to use the environments. To counter that, the seekers, the hiders, learn to defend their ramp. So they either take it inside their fort or they lock it in place, as they know that only them can block objects, being one of the rules of the game. And finally, as a last resort to counter that strategy, the seekers learn bug surfing after only 500 million of iterations. Bug surfing is basically an exploit in the game. The agents learn that they can move around objects while being on top of it, so they use the boxes as ramp. They go on it, and then they move it towards the fort to jump over the wall. I believe that with a lot more billions of iterations, the agents could find more bugs to exploit and reach their goal of winning the game. When it comes to making AI learn more or less autonomously, there are two popular approaches, being self-play and intrinsic motivation. For this study, the goal was to see if AI can learn by itself to develop human traits. So we'll compare the two methods and we'll see why I chose self-play here. So the learning driver of self-play is competition, while intrinsic motivation is curiosity. Intrinsic motivation encourages its agents to explore the environment. Keep in mind that both those approaches is programming, so you code how the agent should broadly think, and then you put them in here I choose a game and see what they develop out of those boundaries slash method on how they should think. So the behavior of self-play is goal-oriented, meaning that you, in my case, either win the game or lose it, while intrinsic motivation is rather unfocused. So in this research, I would have programmed that the main goal is winning the game, but I would have rewarded like points, I will say, for exploring the map, which often leads the agents to forget their primary goal and just do exploration. For self-play, the skills developed by the agents can be adapted to other context. We'll see later how that works. While in intrinsic motivation, it's rather difficult. As they forget the primary goal, they develop skills to just explore, which is not really useful in other contexts. So the skill adaptability makes self-play easily scalable, while intrinsic motivation is not, because the more complex the environment, the more time they'll spend to explore it, and less time they'll try to actually find strategies to reach their ultimate goal. One of the key challenges for self-play is that it requires significant computational resources. You need hundreds of millions of iterations to see tactics developed by the agents, as I said earlier, for my particular case in the study. And intrinsic motivation requires carefully rewarded structures. So you want to reward the agent to explore its environment, but you don't want it to lose focus on the primary goal. So it's really kind of tricky. What we want from AI in real-world application is for it to transfer skills developed for one specific task to other ones. I wanted to see if the agents who played the game hide and seek through self-play could achieve that, which is why I created 5 tests. So I made them play in these tests, as well as newly created agents who didn't play the game hide and seek to compare the two. What I saw is that the agents who played the game had way better results, demonstrating that self-play is a good method for making agents learn because they can actually transfer those skills to other tasks. The most significant outcome of this research is the demonstration that complex human-like behaviors can emerge naturally from AI, even when given simple objective. The key to achieving this is competition, because it makes the AI create what we call an autocurriculum. I think the work I did here can be a reusable foundation for future one. The research in the field looks promising. I think it's quite easy now to make the AI learn by itself. What we should do is create a better neurological network as a base for the AI to think, because 500 million iterations for the AI to learn to bug surfing is quite a lot. Although the need for further research is very clear, This work represents a significant step when it comes to building AI models that are both autonomous and adaptable. I hope I made you interested in how promising AI is when it comes to self-learning. The journey is just the beginning, and the possibilities are truly limitless. Thank you for your time.